Today's speaker is Konstantin Mischaikow, who will be speaking to us about nonlinear dynamics in an age of heuristic science.
All right, thank you very much. And so this is very much kind of a talk of work in progress. I'm going to try not to lie to you, but a lot of what I will be saying is really work in progress. I'll try to keep it honest where I think it's just technicalities that need to be dealt with, and places where it's essentially wide open and I'm just guessing. So I hope you'll put up with that. Let's see. Why am I not advancing? Oh, there we go. Got it. Okay. So this really, motivation for this really comes from work that I've been doing in applications, which is what I think this seminar is all about. How do we use algebraic topology in applications? And so I'd like to start with just a modeling question. And if I give you this picture and I say, what's going to happen in the future from this picture? So what's the dynamics associated with this picture? We know what to do. I mean, we sit down and we write down Newton's equations. And then we say, if you want the answer, you've got to tell me what the masses of these planets and suns are. And you've got to tell me what their current position is. And you've got to tell me what their velocity is. And then, well, we'll solve the equations and we'll do a pretty good job of keeping track of things. I mean, it's complicated. It's very difficult to, the three-body problem is still being solved, being studied. So, I mean, I don't want to say that this is trivial, but the modeling question is resolved kind of on the crude level that I'm talking about. Here's another, picture, and I would like to do the same thing. So what you're looking at here is a gene regulatory network. This is for the RBE2F signaling pathway, which exists in mammalian cells, and it just tells the cell whether it should reproduce or not. So it's very much related to dynamics. And then the question is, well, what's the differential equation? And in this sense, Newton, we just can't hope to have anything like Newton's laws, where we're all going to sit down and agree on what the equation should be. And the reason is because this is unlike, quote, the simplicity of planets running around Newtonian gravity. This is a very, very much a multiscale system. Every one of those arrows that's in that diagram represents a massive amount of chemical reactions with lots and lots of different participants. And then these participants interact on different time scales. So there's really, I think, no hope to write down a differential equation that would give us the kind of quantitative assurances that we get out of Newton's laws, right? But the reality is this is a really important problem. I mean, this RBE2F network is associated with the majority of cancers at least in humans. And so, it's the kind of thing that we would really like to understand. And so that's kind of what this talk is about. How do we do differential equations in a setting where it really doesn't make sense to kind of universally write down a right-hand side, all right? So, okay, and what I want to kind of convince you is that I think that the language of algebraic topology might be a better language in which to try to understand this, at least as a first pass, than traditional methods of doing dynamical systems. Okay, so having said that, what I'm really going to start off with is trying to give you a different definition of dynamics, all right? And to do that, I have to give you a little bit of background. I don't know the it's a fairly large audience with, I think, disparate backgrounds. So bear with me when I tell you what for some of you might be absolutely obvious, and maybe for some of you is completely unknown, just because it's a different different field. All right. So the first algebraic primer I want to give you has to do with from order theory. Okay, so we're going to start with a partially ordered set. All right. I assume everybody knows what that is, but there's a picture at the bottom. And if you give me a partially ordered set, then I can always make a lattice. And a lattice I'm going to think of as an algebraic object with two operations. In this case, I'm talking about the lattice of downsets. So I pick a, oh, I can't see my mouse. So I pick a, maybe the element B, and I look at B and everything that lies below it, which would be the set AB. And then there's a lattice where you have two operations, which are intersection and union. All right, and I've drawn that lattice and I've denoted it by OP. I've drawn that lattice, and that also is a partially ordered set with respect to inclusion. If I start, on the other hand, with a lattice, so here's now this, and I'm going to assume that people understand lattices. If you don't, then just keep in mind this operations of intersection and union. I'll use some different operations at some point, but that becomes a technicality. So if I start with a finite bounded distributive lattice, then there's a special poset within that lattice that I can look for. And that's the poset of joint irreducible elements. So I've defined these joint irreducible elements in terms of the algebraic structure. But another way to look at them is to say that these are the elements of the lattice that have a unique immediate predecessor. And so I've labeled those in red. And I told you that this lattice has a poset structure coming from inclusion. And so if I restrict now to the elements that are labeled in red, and I look at that poset structure, then you see a poset that has exactly the same structure as the poset that we started with. All right. And this is not a coincidence of this example. This is Birkhoff's theorem. And this is, in some sense, what started lattice theory as a mathematical theory is this theorem. And what it says is if you start with a finite distributed lattice and you look at the poset of joint irreducible elements, and then you look at the downset, you end up with a lattice that's isomorphic to the lattice you started with. And the other statement is that if you start with a finite partially ordered set, you look at the lattice of downsets, and then you look at the poset of joint irreducible elements in that lattice, which is what we did, then you end up with a poset that's isomorphic to the one you started with. What I want you to take away from Birkhoff's theorem is that I can talk either about lattices or I can talk about posets, and there's a way to go back and forth. So they have equivalent information. And this really does have something to do with dynamical systems. I will get there. All right. I really should have been telling you about Priestley's theorem, because actually, if you want to carry out all the theory that's associated to this, well, the dynamical systems are complicated. Things actually take place in, there are infinite lattices and things like that. But that's for the experts. All right. So Birkhoff's theorem is all we need for what I'm going to talk about today. So the second point in the algebraic primer is something that I'm pretty sure everybody here knows about, and that's the notion of a cell complex. So this is just a purely combinatorial way of talking about the basis of homology. So we have a cell complex. It itself is a poset with the face operations being the ordering. You have a dimension function that tells you the dimension of the cells, the elements in the cell complex, and you have an incidence number. And because of statement 3, the incidence number is just a way of codifying the fact that you have a boundary operator. All right. So anytime you have a cell complex, it generates a chain complex. And so if you prefer, every time I write this down, there is this cell complex that we're working with, this chain complex that we're working with. It's just that these are in essentially different categories, right? The cell complex really is a combinatorial poset structure, whereas with this algebra on top of it. But the chain complex I really will be thinking of as a collection of, in my case, linear algebra, because I'm going to restrict myself to a field, all right, for today's talk. So here's just a fact. This is a trivial thing to check, that if you think of the cell complex as a poset and you look at a down set in that poset, no, the lattice of downsets in that poset, that lattice, all the elements of that lattice will form a cell complex. And then there's one more lattice I want to talk about, and that's the lattice of closed subchain complexes. All right, so I've moved now from this cell complex. I'm passing to the linear algebra level, and so this also is a lattice. Here's where these two algebraic operations, which used to be intersection and union, have now changed. I still maintain intersection of the vector spaces, but the union gets replaced by span. Okay, so again, if you've seen this before, then this is boring, and if you haven't, it takes you 30 seconds to 10 minutes to convince yourself that this is correct. I'm closer to the 10-minute level. So one more comment is that I can talk now about a lattice filtered cell complex. All right, so this is just a cell complex, but I'm going to keep track of elements of this cell complex or subpieces of the cell complex by distributive lattice. So I have this distributive lattice L, and I have a lattice homomorphism that goes from the lattice into this lattice of closed subchain complexes. All right, so again, I really haven't done anything except tell you a bunch of definitions. Okay, so now what I'd like to do is to define a notion of dynamics. All right, so I will eventually talk about how this relates to dynamical systems, but I want to define dynamics, and maybe it's a good place to make a point of perspective here, right? When Newton wrote down his laws of differential of motion, they were written as differential equations, and when people solved the differential equations, the idea was that you produced a function whose derivative satisfied the right-hand side of the equation. All right, and that worked well for a long time until Poincaré was working on the three-body problem and realized that that was not a particularly effective way to describe the dynamics. The dynamics was just too complicated. You could write down power series expansions, but for all intents and purposes, those are completely impractical. I mean, in that case, it's just because their convergence rates are so slow that you don't get meaningful information out of it. So he introduced these what we today would call dynamical systems. The idea that what we should focus on are geometric structures. Are there periodic orbits? How do the periodic orbits relate to each other? And the notion of invariant set became the dominant notion. It wasn't the particular differential equation. Two dynamical systems were equivalent if they had the same set of invariant sets. What we learned in the latter half of the last century was just how complicated that was. If you try to classify things up to invariant sets, it's basically, this is not something that's decidable. It's just too rich. And we see in bifurcation theory, which again is an incredibly rich structure, bifurcations can take place on all scales. And so trying to understand dynamics on the level that Poincaré was suggesting, I would say that we kind of came to the same conundrum, that it too is incredibly rich. It's much less rich than actually writing down an explicit solution, but you're asking for maybe far too much information than would be accessible for a typical problem. And so what I want to do is I want to talk about an incredibly crude notion of dynamics. But I don't want to start with the idea of a dynamical system and think that I'm making it crude, in part because if you think of this modeling problem from the biologists, they give you the network and they say, this is my model. They don't give you a right-hand side. They don't tell you properties of the right-hand side. And, network science is, there's lots and lots of things that are being represented as networks. that involve dynamics. And the goal here is to be able to just look at the network that somebody's given me and say, okay, here's what you should expect with respect to the dynamics. All right, so I need a notion of dynamics that easily absorbs that as the input. Okay, so that's what I'm going to try to do now. Okay, so, and this is where I'm going to use the material that, you know, the 3 slides of definition. So I start with a cell complex. All right, so I'm really thinking about starting on a purely combinatorial level. That's why I started with a cell complex rather than a CW complex or a geometric realization of a simplicial complex. So I have a cell complex, and I'm going to define a dynamic clade, and this is going to be my notion of dynamics, to be a bounded sublattice that's given in terms of the top cells of this cell complex. All right, so think of a finite cell complex, and so it's going to have a collection of top cells, and I'm going to choose some bounded sublattice of that. With the extra constraint that this bounded sublattice gives rise to a lattice filtered chain complex. All right, and so that's now my notion of dynamics. I put a star in this definition. I'm really thinking about ODE dynamics when I do this. If I was talking about the dynamics generated by maps, then I would have to, on top of this, give you the action on this lattice. All right, and that's just an extra level of complications. There's still some fundamental work that needs to be addressed, but I think the same ideas can go through, except you're going to have to deal with this additional action. All right, so again, this is at the level that I've given it, it's purely combinatorial. Now, in practice, when you're going to use this, you're almost certainly going to have some kind of concrete geometric realization of this cell complex, right? The cell complex, for example, could give rise to a CW complex, and the CW complex is sitting in a space which would be the natural space in which you want to do your dynamics, all right? But for the moment, I can just talk about it in a purely combinatorial language. And I think that's very useful for the computation part, all right? And again, I will try to make it clear that I think this is a computationally very effective theory. Okay, so that's the definition. Now, there's a couple of things that immediately come out of this definition. So we're talking about lattices, and I just told you that Birkhoff's theorem is a fundamental way of understanding them. And so there's going to be the post set of joint irreducible elements, and I'm going to call that the Morse graph. Actually, to be correct, what I'm really saying is the Morse graph, when I draw pictures of it, is the Hasse diagram for that post set. Right? But if you give me a lattice, finite lattice, everything's finite. I should have had finite in the upper part. Then I have that associated Morse graph. What I will actually much later on be doing is talking about Morse graphs, and then from that, because of Birkhoff's theorem, there will be this dynamic clade that's associated. But that's just because of today's talk. I think if we're starting from data-driven dynamics rather than heuristic model-driven dynamics, then we would be much more interested in starting on the sublattice level. If I take any element in this post set, then there's going to be something I can call a Morse tile. And you know, the post set of the joint irreducible elements, that means they have a unique immediate predecessor. And so the Morse tile is look at the lattice elements and take that are associated with that in the lattice of down sets, and take away its immediate predecessor. And that's going to give you a set of elements. And those are what I'm going to call Morse tiles. We're talking about sublattices of, we're talking about, because I have this lattice homomorphism, I can talk about the, and here I made a mistake. There should be a lambda A and there should be pred of lambda A. All right, so, or lambda of pred A, right? I've now moved to the cell complexes, and so I'm taking the homology there, all right? And so I can take this relative homology, and I'm just going to declare this to be something called the Conley Index. Right? what you should think from the dynamical systems point of view is that the poset structure that we're getting out of the Morse graph, this is going to capture the gradient-like dynamics. So this is the dynamics that, you know, you start with your initial condition and you follow it forward in time, and it never comes back close to where you were. The Morse tiles, if there is stuff that's coming back, if you have fixed points, periodic orbits, chaotic invariant sets, then that's all going to be captured inside these Morse tiles. All right. Okay, so I think it's a very simple definition, and now I've given you an object or a collection of objects, and I've told you here's some algebraic topology that you might want to compute. I think all of us who are in this group here have no trouble dealing with these kind of homology computations. Okay, so this Conley index, well, I declared that to be the Conley index, but the Conley index, of course, really starts from dynamical systems. And there are a lot of theorems that say that if you can compute the Conley index in a dynamical system, whatever it is, then you can get a lot of information about the underlying dynamics. So there are theorems that say that there are fixed points or periodic orbits. There are theorems that tell you about kind of the global structure of gradient-like structure of dynamics. There's theorems about chaotic dynamics. So I'm not going to go into any of these details. I'm just telling you that there's now a library of results that says, oh, if I could get my hands on the Conley index, then I could tell you something about the dynamics. And typically you need a little bit more than just this homological Conley index. You typically need some other information like a section or disjoint elements or something like that. But the claim I'm making is that just the algebraic topology via this Conley index in the form of homology, it's sufficiently powerful that if I could somehow get my hands on this Conley index, then for a dynamical system, then I can tell you something about the underlying dynamics. Okay, so what I told you when I defined the dynamic clade was that there was a way for me to pull out something that I called the Conley index. And what I haven't told you yet is what does this notion have to do with classical dynamics? So that's what I want to do next. So let's start with a compact metric space. We can move to locally compact, but then, you know, there's small technicality. So I have a compact metric space, and let's make it a nice metric space so that it actually is a CW complex. And so let's take a regular CW complex decomposition of X. So I'm representing now X in terms of this regular CW complex. And I take a compact, so a definition now, a compact set in the metric space is an attracting block if under the dynamics, so think of this as the flow given by solving the differential equation. If you take that set and you move it forward in time, then it's strictly interior. It lies strictly interior to itself. All right, that's what an attracting block is. Here's a proposition. The set of attracting blocks is a bounded distributive lattice. All right, so there's a series of papers that I've done with Bill Calise and Rob van der Voort where we really explore the representation of classical notions of dynamical system in terms of the algebra of lattices and posets. So for example, we can prove that any attracting block is going to be a regular a closed regular set. Not necessarily, it depends on whether we have enough structure for a CW complex, but let's keep it simple. And then there's a bunch of theorems that we have about if I gave you a dynamical system and certain aspects of the dynamical system, could I approximate it using a nice CW decomposition? And basically the theorems say, yes, you can always get an appropriate approximation. So on one level, you're not losing information. That's a lie. You have to talk about things like Morse decompositions and lattices of attractors. Again, I don't want to go into that detail, but when you talk about that level of the dynamics, then these approximations can recover that in a very general setting. So what these papers say is that I'm really not losing much information by thinking about it on this level. So if I gave you a lattice, a sublattice of these attracting blocks, because the actual lattice of attracting blocks typically is uncountable, all right? But let's choose a finite sublattice. Then, well, if you just check, it turns out that that will be a dynamic clade, all right? So I know how to go from differential equations and the structures of differential equations to dynamic clades. And now we can ask what happens when you go back and forth. So if I give you a dynamic clade, then actually I'm defining an enormous family of differential equations for you. Basically, if you think about, what's the statement of an attracting block? I have a compact set and I want that the dynamics moves it inside itself. Just think of that as a transversality condition along the boundary. So I give you a finite lattice. I'm saying any differential equation where the vector field has this nice transversality condition on the boundary of these finite sets of these finite collection of sets that forms my lattice of attracting blocks, any one of those differential equations is now going to fit inside this dynamic clade. All right, so the dynamic clade is a way of talking about huge families of differential equations where I don't need to write down a right-hand side. And what I also have is, and now this requires a theorem, but that's not difficult to prove, that if you use my notion of a Conley index and you go back to Conley's notion of a Conley index, they're exactly the same in this setting. All right, so we started with this combinatorial object. We did these very simple algebraic topological computations. And I'm telling you that if we had been working with a dynamic clade for a geometric realization of a differential equation, we've already done all the computational work in order to identify the dynamics. Going the other way, if I give you a dynamical system, well, like I said before, the lattice of attracting blocks is typically uncountable. So when you pick a finite sublattice, you're kind of choosing a level of resolution. And it's quite possible that you will get different lattices of attractors if you choose finer and finer resolutions. So a particular dynamical system can give rise to infinitely many dynamic clades. This is your ability to go in and choose the level of at which you would like to understand the dynamics. So let's now move to modeling based on these ideas, all right? So this is what the biologist would give me as a model. And I would now like to say, okay, there's machinery, and I'll talk about that machinery, very explicit software that allows me to go from this picture into the dynamical system setting that I've given you. So the fundamental assumption I'm making is that the dynamics can be expressed via differential equation. I'm going to think of the nodes in that graph as representing some, well, I'm coming from biology for these motivations, so think of it as a quantity of a protein. And the basic modeling assumption I'm going to make is that that these proteins, the amount of protein I have is a balance between a decay of the proteins and growth of the proteins, production of the proteins. And these are controlled. Well, the network tells me how they're controlled, and there's some kind of nonlinearities that guide what's happening. And my goal here is to identify a dynamic clade that represents the dynamics of this. So I'm not after a particular differential equation, I'm after a dynamic clade. So to do this, I need a cell complex, and I've got to come up somehow with functions gamma and lambda that are going to be compatible with a cell complex so that I can do these computations. And it should, of course, be compatible with what the biologists are thinking about when they wrote down that network. Okay, so this requires a modeling choice, and I'm going to talk about the modeling choice that we have. This same kind of machinery can be done with different modeling choices, and I just want to mention that Kaczynski, Morozik, and Vonner and various sub-collections of them have been working on something very similar in spirit, where they have what they call Foreman complexes. That would be a different modeling choice, all right? So basically, I showed you these complicated diagrams with arrows. So here's a little piece of it where the arrow is blunt. In other words, I'm telling you things get repressed. And so I need to pick some kind of model to represent that. And so I'm going to choose the simplest one I could think of, which is a step function. Because it's a repression, that step function, take a downward step. If it was a pointy arrow, the biologist would say that's activation, so it would be an upward step. Do I know what this function is? Only that it's a step function, and then there are a bunch of parameters that come into play that tell me which particular step function I'm going to work with. I'm going to have to work with all these parameters. The important thing is that if there's going to be change in the dynamics, it's going to change at the thresholds. And so the thresholds are going to be where I care what's happening. And of course, things are going to be more complicated. Here's an actual model that the biologists care about, and there's lots of interactions. And so these gammas and lambdas that I had, I'm going to make them sums and products of these elementary types of step functions. Phase space, well, it's going to be, in this case, for this model that I have on the left, this P53 model, the phase space would be 5-dimensional. I'm going to have to tell you somehow what these arrows, how they interact. So I end up with a sum or product of these step functions. And I use those thresholds at which things change to define a cubical complex. All right, so that's my cell complex that I'm, okay, that's the first iteration towards a cell complex that I'm going to use. All right, so let's just call it a cubical complex. And I'm going to care where parameters, the set of parameters, I want to study the dynamics under all parameters, where the growth and the decay is not 0. All right, now that masks the simple idea that's going on. So if I went back to this very simple setting, then what you can see is that depending on those parameters at that threshold, I'm either going to have something that's greater than 0 or less than 0, and it depends on whether I'm to the left or to the right of that threshold. And so, the arrows indicating greater than or less than, I get all possible combinations in principle. But I want you to notice that the set of parameters at which a particular inequality holds is a semi-algebraic set. All right, so I've now given you a nice way of decomposing a parameter space. And I'm going to organize this decomposition into something called a parameter graph. The nodes are going to be semi-algebraic sets, and the edges are going to indicate that I have 2 semi-algebraic sets where they're defined by exactly one change in the inequality. Let's go back, because this is how I'm going to define dynamics. I want to know, because I'm talking about my dynamic clade, I'm after my dynamic clades. I've got these top cells now, which are these cubes, and I'd like to know how one cell goes to the other cell. In the case where both arrows point to the right, it's pretty clear that the left cell should go to the right cell. In the case where everything's going to the left, it's clear that the right cell should be going to the left cell. What should be done in the middle? Okay, I've made a decision. I'm going to talk to you about the software, but I don't want to get hung up on this because I want to come back and do it right. Okay, so we've written software, and this has been around for a while now, DSGR, and dynamic signatures generated by regulatory networks, that does exactly what I've talked about. You give me a network, it recognizes what the phase space is, it looks at the parameter space, it does this decomposition of the parameter space, and then it computes all the dynamics. So what does that mean? Well, there's 803,520 nodes in this particular parameter graph. So that's the number of semi-algebraic sets in which those inequalities divide the parameter space. And so I want to go through for every one of those nodes, and I want to compute, I'm going to compute a Morse graph, right? A Morse graph is a poset. A poset is going to be equivalent to a lattice of downsets, all right? So I'm going towards a clade. And because this is purely combinatorial computations, it's extremely fast. So to go through all those 800,000 nodes takes 37 seconds on a laptop, all right? So I've just now solved a 5-dimensional differential equation over a 29-dimensional parameter space in 37 seconds, all right? Is this useful? Well, in this paper, the interest of the people there is the fact that oscillation seems to be what's driving control in the system. So we could ask, well, does this particular network give rise to oscillations? give rise to oscillations. Those should be the oscillations you can observe. Those should be the minimal nodes in the Morse graph, because that's kind of the most stable region. So I can ask, are those nodes associated with oscillations? And the answer is, yeah, in about 7,000 of those nodes, of those regions it is. So you just kind of get to look up your answer. All right, so you get instantaneous answer to this question. And you can now ask, well, I'm in a 29-dimensional parameter space. Where are these parameters? Okay, I've given you an explicit list of what the inequalities are, so you know explicitly where they are, but 7,000 explicit answers is kind of useless. You could ask what's kind of the geometry of it. Even that's probably too hard, but you could ask about the topology. And it turns out that this collection of 7,000 nodes is contractible. All right, so the reason I emphasize this is that we're now computing homology for an explicit complex in 29 dimensions. All right, so these homology computations, we now have enough machinery so that we can talk about reasonably high dimensional spaces and have explicit information about the topology. Okay, let's go back to this point. I had those question marks in there. The reason I can't really resolve it properly is because the cell complex that I'm using, the cubical complex, is too small. I need to blow it up. And so that's what we're working on right now. All right. So and I think most of this is I think we have a good understanding of what we're doing, and there are technical issues that we still need to overcome, but I think we're in pretty good shape here. So blow up that cell complex so that every cell in your cubical complex becomes a top dimensional cell. And then, while we have software, and I'm not going to go into the details, actually figuring out what direction the arrow should be is non-trivial work. But here's a simple network. The parameter space here is 18 dimensional. Now you have a picture of the parameter graph. It's simple enough. I can draw the parameter graph. And here are the equivalent of phase portraits in this cell complex. So what you're looking at here in this blown up cell complex is, you know, an instantiation of the Morse graph that sits there. There's an unstable object that you might think of as a fixed point that goes to two stable objects. So there's bistability that's seen. And if you walk to a different node in the graph, these are three of this one on the left, I think is well, I'm not sure which node goes, which picture goes to which node, but these are taken from some of these red nodes in here, right? And so you can kind of see how the dynamics is bifurcating as you walk through this graph, all right? So we now have kind of an understanding of this three-dimensional dynamical system in 18-dimensional space, and you know, these are the equivalent of phase portraits. Okay, so just to summarize, this was my definition of dynamics. What I gave you was a Morse graph. I'm claiming a theorem that I've actually, if I go and look at the lattice of downsets, I've actually defined a dynamic clade. So from this perspective, the easiest entry point is through the Morse graph, and we get these dynamic clades, and so we can start doing the algebraic topological computations, all right? And that leads us now, well, we're doing homology essentially, and how much information do I need to keep around? This cell complex I showed you is fairly large. The Morse graph is very simple. On an algebraic topological level, could I get by with something as simple as a Morse graph? All right. And the answer is yes. All right. So this is a new chain complex that one can construct. The boundary operator of this chain complex is called the connection matrix. This idea is not new. It goes back to Bob Franzosa, who did this in his thesis in the 80s. There's picked up and done by Joe Robin and Dietmar Salomon in the case of maps using this kind of lattice language. But more recently, especially Kelly Spenlove has kind of refashioned this theory, but in the context where we're really doing it with these cell complexes. And so we now have a very computable theory, and Kelly has been doing these kind of computations on cell complexes with trillions of cells in 10 dimensions. So it's very computable. So what we have now is a homological representation of dynamics, and we would like to see whether that's useful, all right? So for this particular example, this would be the boundary operator, where I've tried to do the color coding. I've picked out the non-zero generators of this the cells, and that would be the boundary operator. All right, so I know I'm at the end of my time, but let me just give you kind of a window of where we're going. All right, so now I'm kind of in speculation land. I mean, the picture I'm going to show you is, I understand because I can do it all by hand, but the general theory is something we're working out with a variety of people: Kelly Spenlove, Everton Vieira, Marcio Gamero, Tomas Gideon, and others. Okay, so I want to go back to something very simple, the toggle switch. This is supposed to be a switch. It was the first synthetic network that was built. There are the inequalities on the left that define the parameter space. The phase space is 2-dimensional. Parameter space is 8-dimensional, all right? So you make your cell complex. Here's the particular parameter graph. What I've done for you is, the parameter graph breaks up into 9 regions in this 8-dimensional space. I've given you explicit inequalities for the parameters. And for each one of these parameters graphs, I'm showing you the Morse graph and the Betty numbers for the Conley indices. All right. I'm giving you one more piece of information, and that is, where is the Morse tiling? So there's Morse graph, which has one element there, and the red dot says that it's the lower right-hand cell that contains the Morse tile, and this is where they are for the other cells. Okay. What I can do then, I can compute connection matrices, and this would be the same information, except now I'm just giving you the boundary operator. So I'm giving you the cell complexes at those particular regions. As soon as I give you cell complexes, a family of cell complexes, so a family of chain complexes, the first thing to do is to say, well, gee, how are they related? They should be related by chain maps. And here I've written down all the chain maps that relate those cell complexes. In the Conley theory, these are called transition matrices. All right. So I've given you 9 complexes, chain complexes, and a bunch of cell chain maps that tell you how they relate to each other. Why do I care about doing this? Well, what's a switch? This is engineering 101. This is what a good switch is supposed to do. If you're going to go, you've got a control, you've got a knob you get to turn. If it's on when the knob is low and you turn it up, then what's supposed to happen is eventually you switch into the off position. But when you turn it back down, you don't immediately go back into the on position. You go in the off position for a while before it flips to be on. All right. Okay, so this is the picture you see in physics textbooks or engineering textbooks. How do we represent this in a purely homological fashion while guaranteeing basically all this information that we care about? So in this case, well, I've got a gene, and gamma is a constant that tells me how fast things are decaying. And you can pour chemicals into a cell and you can make those proteins decay faster. So that would mean that I'm making gamma 1 get larger because there's a minus sign. That's why the inequalities move the way they do. So I'm passing through this with making gamma larger. So, well, what's the dynamics associated to that? Well, if I start in the left-hand parameter region, that's where that node is. As I move to the middle one, I get to this bistable setting, but the algebra tells me that that generator from the lower right-hand box actually maps to the generator of the lower right-hand box. So if I was thinking about that dynamically, back to my picture of hysteresis, I've started in the on state. I'm measuring now that vertical axis as a measurement of the x1 value. And I've moved and I've stayed in that region. That's what the algebraic topology is telling me. If I keep going, well, again, there's a chain map that tells me what generator I get mapped to. And now I get mapped non-trivially onto this generator. So that's what the dynamics is doing for me. Well, let's go back. All right. So I go back. And what you will notice is that if you do that composition, going forward and coming back is not the same as just having gone forward. And that's because when you come back, you end up in a different branch. All right. So the algebraic topology in and of itself is enough to talk about the kind of structure we want. And the Conley theory is enough to tell us that this is actually something, even though we're just doing homological computations, this is actually what you would see in the dynamics. The final thing that I want to say, and I apologize, I thought it would be a little faster, is that, you know, here are a bunch of models that a biologist would typically write down if they were going to write down differential equations. Okay, DSGRN, and we're writing down theorems right now to prove this, that if we're at an infinitely high or close to an infinitely high, then we really have dynamic clades, so we actually have theorems. Here's an interesting phenomenon, and I'll just show it to you, and I'm open for people who can try to suggest how you might turn this into a theory. So if I start in the upper right-hand corner and I follow, you know, go left and come down, I have some algebra. If I do it the other way, I have some algebra, and they're not the same. But the parameter space is nice and contractible. But now I have two very natural sets of morphisms, and they don't commute. That suggests that there must be some kind of singularity happening at some point in parameter space. And the simplest way to resolve this is the Cusp bifurcation. Now, people who do dynamical systems, it typically goes the other way around. This is catastrophe theory. You look at the singularity, you understand the unfolding near the singularity, and I'm saying we can do it from the other direction, but I don't really know what that means mathematically, all right? The conjecture, and this is work that's being done by Shane Kepley and Helena Quirello, and they're trying to do it numerically because, again, we don't really know how to do this on a mathematical level, is that if you look at these Hill function models, then obviously parameters change as soon as you start changing the D, the actual parameter values. But this global structure of how the dynamics is put together, we believe that that's invariant, all right? So again, I apologize for going late. I want to emphasize that this is very much a joint effort with many, many people. Thanks.
Thank you. Everybody, please unmute yourself and applaud our speaker. Okay, so do we have any questions for Konstantin?
Too much, too fast?
Feel free to unmute yourself, or you can ask it in the chat. I'll give everybody some time, a few minutes to.
Hi, Konstantin.
Hey.
This is Faye. Hi. I just have a, kind of, I think it's a pretty naive question, but towards the end, when you have this diagram where it's no longer commutative, and
Yes.
Your conjecture is that there is a cusp phenomenon going on there. Is that certain, or like there's a cusp bifurcation? Do you think this is actually indeed the case, where if you see this kind of phenomenon in your diagram and it does imply there's a cusp bifurcation? Is this a bijective thing, or it's just a highly conjective?
Okay, so I haven't actually done the computations for the Hill functions, but I'm certain for the Hill functions that that's what's going on. All right, because well, it's easier if I do ramp functions. If I instead of putting that smooth nonlinearity, I just have a function that's I got the two high points and I just put a ramp there. Then I can actually show you explicitly that it's a cusp bifurcation, right? In Hills, I think I'd be shocked if it wasn't a cusp bifurcation. And in fact, here, I think there's a 6-dimensional surface of cusp bifurcations going on. But that's because I've given you this particular differential equation, and I can, grind through it and drop lots of pictures because it's 2-dimensional. What happens in the higher dimensional models, I really don't know, all right? But the fact that you don't have commutativity really means that there must be a singularity there, all right? So I think this is a completely open question. Like I said, I mean, catastrophe theory is well, it's René Thom, right? He says, look, you have essential singularities. We understand we can work out unfoldings around them, and then the dynamics I've told you what's going to happen to the dynamics in a neighborhood. So that's kind of local to global, but global in a very, very minimal sense, right? Here, it's completely the opposite. It's extremely global. I don't have, this is true for anything that belongs to this dynamic clade that I've created, right? So I really, it's to me, it's a completely open question. And the most natural thing for this simple example is to say, well, there should be a cusp bifurcation. But if I, in general, as soon as I see non-commutativity, there has to be some kind of singularity. And my question is, how do we represent those singularities in a meaningful way? Yeah,
yeah, I think for me, this is really exciting, a way that somehow you have this very combinatorial structure, and the conjecture seems that if you find this sort of local inconsistency with respect to this commutative thing, you can use a combinatorial structure to try to detect singularities. And that seems to be quite exciting. But yeah.
Yeah, I think it's very exciting, but I don't know. I've never seen theorems to that effect. All right, so it's completely open.
All right, thank you.
Yeah.
So we have a question in the chat from Massimo Ferri. So the question is, in catastrophe theory, there's a powerful classification. Do you think there will eventually be something like that in your combinatorial version?
Let me hedge. What the Conley theory has is that's nice is that it actually has a sheath structure to it, right? And this goes back to work of Montgomery in the 70s in his PhD thesis. And I know that there's a very, very soon to appear preprint by Bill Calise and Alex Dowling and Rob Vandervorst on talking about the sheath structure for lattices of attractors and things like this. So this lattice theory, putting it into a sheath structure theory. So there, so I think that in that sense, that's a way to organize this information more, kind of more abstractly than I have done in this very concrete setting. I think there's still room to do the sheath structure for the algebraic topology and things like this. But I think that's going to be the level of organization, right? I think once you understand what can be done combinatorially with respect to that sheath, whatever restrictions there might be there, then everything else is possible. All right. But that's, again, pure speculation. All right. I think what's interesting, is if you think about catastrophe theory, right, that you do lose very quickly as things get more complicated, that nice classification scheme, right? And I'm saying, well, this machinery keeps on working. So, this machinery must be putting a lot of stuff under the carpet, right? And that's part of why I really don't even know how to answer Bayes' question. I mean, I don't know that if I saw this for a different family of differential equations that satisfied the clade condition, I don't know how to prove that there has to be a cusp bifurcation. Right? I mean, you would think that should be possible, but I really don't even know how to get started there. I believe that that's the case, but I don't know how to prove it. right? So I think it's cool. All right, that's how I would like to endorse it. And if anybody has any ideas and wants to talk to me about this, I would love it, because I'm kind of at a loss as to how to make the next steps forward. It just seems very, very daunting. And yet we have this machinery that, you know, that can produce enormous numbers of examples. All right, that is, you know, very, very new. I mean, nobody's been able to do these kinds of understanding of bifurcation. Well, we aren't really doing bifurcation, we're kind of, again, because of the sheath structure, we're kind of sweeping it under the carpet. But I don't know of anybody else who can work in high dimensional parameter space. And we have machinery that does it for you. So you want an example, we can put it together, and you can do it very quickly, right? So there's immense amount of data if you want to start trying to understand a classification or something like that.
Thanks, and Massimo says thanks as well in the chat. Question from Phil Fleming. Do you think these methods can be used to study the dynamics of convergence in neural nets?
Yes. That's the short answer. We're actually trying to see right now, this is work I'm doing with Bill Calise and Marcia Gamero and Mohammed Asali. We're really trying to see if we can use this to understand something about you know, deep learning. I mean, there's you know, there you've got, you know, networks and something that should be like a gradient flow, and you'd like to understand all the possible minima and how they're related, and, you know, what impact does the training set have on where you're going to end up. So yes, there's nothing here, you know, the dynamic clade is the key point, right? What I'm trying to do with William Coelho and Marcia Gamero is to actually move this into the field of ecology. So you have trophic networks, interactions between species. There's nothing that kind of even looks like a sigmoidal function, or it's rare that you see something that's a sigmoidal function. But if you think about the dynamic clade, and I kind of hinted at this, I mean, we have these results with Bill and Rob that say anything that's that it can be expressed in this language of attractors can eventually be resolved using these lattices of regular sets, closed regular sets. That says that, you know, there's no reason you shouldn't think of this as an alternative numerical approximation scheme. You're not going to get detailed results, but on the other hand, you know, this, if I go back to here, and that's part of why I showed this picture, right? I mean, you know, if you had to, you know, if you gave the student this picture and said, here's some hill functions and here's some steep nonlinearities, say, here's a differential equation, there's an 18-dimensional parameter space, start drawing phase portraits for me. You know, that's terrible. But the biology labs do this all the time. All right, that's because that's how they understand this stuff. Here I'm saying, Marcia told me it takes 4.5 seconds to compute the parameter graph, right? And so once you've got that, these are just, you know, however long it takes to upload the picture, right? So there's, you know, thousands of phase portraits. We can walk through them. We don't even have to look at them. We can use the algebraic topology to do that. But there's nothing that requires a particular form of the nonlinearity. So this should be thought of as a numerical method, I think. But again, we're just starting to scratch the surface of it. Happy to talk to people who would like to go in those directions.